is a lot easier to use than all those formulas. So the turns ratio can also be expressed as a decimal fraction. And this is done on one side, we always have a value of 1. The transformer has a primary voltage of 480 volts and a secondary voltage of 75 volts. To determine the ratio, divide the higher number by the lower number. So you end up with 6.4. So the transformer has a turns ratio of 6.4 to 1. There are 6.4 turns of wire in the primary for every 1 turn of wire in the secondary. When the turns ratio is expressed as a decimal, all the values of voltage, current, and of turns can be determined by either multiplying or dividing by that ratio. In the example circuit, the transformer has a primary voltage of 240 volts and a secondary voltage of 50 volts, 240 and 50. So the turns ratio, divide the higher voltage by lower voltage, 240 divided by 50. So you get a turns ratio of 4.8 to 1. So 4.8 is placed on the left side and 1 is placed on the right side because the primary voltage is greater than the secondary voltage. Next step in this circuit here is to determine the secondary current using Ohm's law. You have 50 volts in the secondary and 20 ohm load, so the secondary current is 2.5 amps. Now, one of the basic rules concerning transformers is that power in equals power out. That means that the volts times the amps in the primary side must equal volts times amps in the secondary side. So in this example, the primary voltage is higher than the secondary voltage. It simply means that the primary current has to be less than the secondary current. Since the primary current must be less, you would divide the secondary current by the turns ratio to determine the primary current. So 2.5 amps in the secondary divided by the turns ratio 4.8 gives you the primary current of 0.521 amps. The number of turns in the secondary winding can be determined in the same basic way. The secondary voltage is less than the primary voltage. This indicates that the secondary winding will have less turns than the primary winding. To determine the number of secondary turns, divide the primary turns by the turns ratio. So you end up with 62.5 turns in the secondary. But transformers don't have half turns. So round off the number of turns to the nearest whole number. In this case, the secondary winding contains 63 turns of wire. And you can go through it again. This time you've got 120 volts, primary voltage, 450 is secondary voltage. So right away you can take those two values and calculate the turns ratio, 3.1 to 3.75, because you've got fewer turns on this side, more turns on that side, 1 to 3.75. So it indicates that there is 1 turn of wire in the primary for every 3.75 turns in the secondary. And then you can go through again. The secondary current can be determined by using Ohm's law. 0.45 amps times the turns ratio would give you the primary current. The secondary current is found by 450 volts divided by 1 k ohm, 0.45 amps. And the number of turns in the secondary again can be determined using the turns ratio. The secondary voltage is greater than the primary voltage. That indicates that there will be more turns of wire in the secondary winding than in the primary winding. To determine the number of turns in the secondary, multiply the primary turns by the turns ratio. 250 turns in the primary times 3.75. So the number of turns in the secondary is 938. Okay, so now Pan Global talks a little bit about three-phase transformers. In industry, three-phase systems are used extensively. Three-phase transformers are common. Three-phase transformer is similar construction to the single-phase shell-type transformer, except that primary and secondary windings are wound on each of the three legs as shown here. In practice, low voltage coils are closer to the iron core and high voltage coils are over the low voltage coils. And there are different ways of winding. Here, this is 37. And there's different ways. The concentric windings, you have so in practice, low voltage coils are closer to the iron and high voltage coils are over low voltage coils, and 38A and B shows one of the alternative methods sometimes used, pancake or concentric winding. Three-phase systems often use banks of single-phase transformers to replace three-phase transformers. The efficiency and cost of single-phase banks do not compare favorably with a three-phase transformer, but on the other end, they can be much more convenient. For example, if one coil of the three-phase transformer breaks down, the transformer must be taken out of the system and replaced. So if you've got one three-phase transformer like this, you got a breakdown insulation, something happens, you get this coil is shot, that whole transformer has to be taken out. If the same thing happens in a three-phase bank of three single-phase transformers, the damaged transformer can opt to be disconnected, leaving the remaining two transformers to supply three-phase loads at 58% of normal capacity until a replacement can be obtained. And that's called element delta. But you can get three-phase power from two transformers if you have to. When you're driving through Owen Sound, anywhere that the building has a three-phase service, you look at the transformer pole, and 90% of the time there will be three transformers up there, three-phase bank. Hydro One utilities almost exclusively use three-phase banks when it's on a pole. If it's a pad mount, it'll be a three-phase pad mount transformer. Occasionally you will see a three-phase transformer hung on a pole, but not as common. So a little bit more, three-phase transformers contain three separate primary and secondary windings on a common core. Using a common core provides better magnetic coupling and improves the efficiency of the transformer. So here the primary winding is red, secondary winding is blue. So on each one of these, we've got the primary and secondary windings. The windings are connected to either Y or a delta. Most three-phase transformers will have at least one of the windings connected in delta. This is done to stabilize the voltage when load is added to the transformer. Recall that line voltage and phase voltage are the same in a delta connection. A Y to Y connection can be used if the load is a balanced three-phase load. The phase and line voltage will remain stable provided the current on each line is the same. So as long as you have a three-phase load here, that all three phases are the same, you'll have the same current on each leg, then a Y-to-Y transformer is acceptable. So this is similar, the calculations are similar to the other, just straight three-phase calculations we did with the alternator. A Y-to-Y connection can be used to provide both three-phase and single-phase loads, provided the electric utility company uses a four-wire neutral to the primary of the transformer. Four-wire Y connection secondary windings are very common in commercial locations. Common voltages for this connection are 208, 120, and 488, 277 volts. So with that Y connection, connecting at the common connection point will give you a neutral where you can have a lower voltage from this point to either one of those three lines. If it was 600 volts in this primary, the neutral here would create 347 volts from one line to neutral. And if it was 208, depending on the number of turns, we had 208 volts on this secondary. Line to neutral would be 120 volts. Large three-phase pad-mounted transformers are often used by utility companies, industries, and commercial customers. And if you look over at Home Depot, any large commercial building or an industrial facility outside, you will see utilities, higher voltage coming to this type of transformer and then fed into the building. Single-phase transformers are often connected to form a three-phase transformer bank. Transformer banks have a disadvantage, is that they are not as efficient as a true three-phase transformer, but they do have an advantage that if one transformer should fail, that one transformer has to be replaced. So in this example, the primary winding of the three transformers have been connected in delta. And the secondary windings have been connected in a Y. So each one, this one here, connected there, the end of this one is connected there, the end of the third one is connected here. It makes it a Y. The primary and secondary windings can be connected in any combination such as delta to Y, delta to delta, Y to delta, or Y to Y. And you can do calculations in any type of combination of these circuits. In this example, a three-phase transformer has at its primary winding connected in Y and its secondary connected in delta. The line voltage connected to the primary is 4,170 volts, and the line voltage to the secondary is 240 volts. The load is constructed of three resistors connected in a Y over here. Each resistor has an impedance of 2.77 ohms. So using the rules for Y and delta, since a load is connected directly to the output of the transformer secondary, the line voltage of the load will be the same as the line voltage of the secondary. So 240 volts here, 240 volts here. Same as in the other type of calculation. The next step is to determine the phase voltage of the load. In a Y connection, the phase voltage is less than the line voltage by a factor of the square root of 3 or 1.732. So line voltage, 240 volts, divided by square root of 3 gives you 138.6 volts for the phase voltage. The phase voltage is voltage dropped each of the resistors that form the Y-connected load. The phase current can now be determined using Ohm's law. So with 138.6 volts, 2.77 ohms, the phase current over here is 50 amps. In a Y connection, the line current and phase current are the same. Therefore, 50 amps of line current is necessary to supply 50 amps of phase current in the load. Phase current, line current the same, 50 amps. And since only one load is connected to the transformer secondary, the line current of the secondary will also be 50 amps. In a delta connection, the phase current is less than the line current by a factor of the square root of 3. The phase current of the transformer secondary is 28.9 amps. So 50 amps here, delta divided by 1.732, you end up at 28.9 amps in the secondary for phase current. In a delta connection, the phase voltage and line voltage are the same. The phase voltage of the transformer secondary is 240 volts. At this point, all values of the connected load and secondary winding have been determined. The next step is to determine the values that apply to the primary winding. So 240 volts line voltage, 240 volts phase voltage because it's delta there. In a Y connection, the phase voltage is less than the line voltage by a factor of square root of 3. Phase voltage of the Y connected primary is 2,407.6 volts. 2170 divided by square root of 3, 2407.6. When determining values of current, voltage, and turns ratio for the transformer, only the phase values can be used. In this illustration, 3 separate transformers have been designated A, B, and C. The Y delta transformer windings have also been labeled A, B, and C. Note that the B phase of the Y connected primary, B phase of the Y connected primary, is actually the primary winding of transformer B. And the B phase of the delta connected secondary is actually the secondary winding of transformer B. All transformation occurs between the primary and secondary windings of the transformer. The primary and secondary windings of the 3 transformers form the phase windings of the 3-phase transformer connection. The turns ratio of the transformer can be determined using the phase values of the primary and secondary voltages. Since the primary voltage is higher than the secondary, it has more turns of wire. The turns ratio, therefore, is 10 to 1. 2407, 240, 10 to 1. A basic rule of transformers is that power in must equal power out. The volt amps of the primary must equal the volt amps of the secondary. Since the primary has a higher voltage, it will have less current. The current will be less by a factor equal to the turns ratio. You got 28.9 amps here. Turns ratio is 10 to 1, higher voltage, lower current, 2.89 amps. In a Y connection, the line current is equal to the phase current. Therefore, the line current supplying the primary of the transformer is 2.89 amps. The calculation can be checked by determining if the input power is equal to the output power. Use the formula for determining the apparent power in a 3-phase connection to determine if the primary and secondary values are approximately equal. There may be some difference due to rounding off the values. So volt amps in the primary is equal to line voltage to the primary times line current to the primary times square root of 3. So you end up with 20,873 here, 20,784 there. It's close enough that it works out. Now you've got 2 3-phase loads. Similar to when you had an alternator here instead of a transformer. So a three-phase transformer contains a delta connected primary and a Y connected secondary. The line voltage supplying the primary is 13,800 or 13.8 kV. And the secondary line voltage is 480 volts. Two loads are connected to the transformer. The first load contains 3 4-ohm resistors connected in a Y. The second load contains 3 6-ohm resistors connected in a delta. So since both loads are connected to secondary to the three-phase transformer, both have the same line voltage as secondary, 480 volts, connected to 480 volts, connected to 480 volts. In the Y connection, the phase voltage is less than line voltage by a factor of square root of 3. The phase voltage of the Y connected load is 277.1. 480 divided by 1.732 gives you 277 here for phase voltage. With 277.1 volts applied across 4-ohm resistors, the phase current becomes 69.3 amps. In the Y connection, line current and phase current are the same. So the line current necessary to operate the Y connected three-phase load is 69.3 amps. Delta connection. Line voltage and phase voltage are the same. So line voltage here is 480, phase voltage is 480. Volts applied across 6-ohm resistors gives you a phase current of 80 amps. The delta connection, the line current is greater than the phase current by a factor of 1.732. 80 times square root of 3, 138.6 amps. The secondary transformer must supply the line current for all connected loads. Therefore, the line current supplied by the secondary is the sum of the connected loads. So the secondary has a line current of 69.3 plus 138.6, 207.9 amps. In the Y connection, the phase current and line current are equal. So the phase current of the secondary Y connected is 207.9 amps. In that Y connection, the phase voltage is less than the line voltage by a factor of square root of 3. 480 volts divided by square root of 3, 277.1. In a delta connection, line voltage and phase voltage are equal. So the phase voltage of the primary is 13.8 kV. Now that you know the secondary and primary phase voltages, the turns ratio can be determined dividing the larger voltage by the smaller. The turns ratio, 13.8 divided by 277. Phase values only, so it's 49.8 to 1 turns ratio. And then using the rules for delta, the phase current primary can determine I primary is 207.9 divided by the turns ratio, 4.2 amps. And in the delta connection, the line current is greater than phase current by a factor of square root of 3. So the line current necessary to supply the primary is 7.3 amps. And again, you can check the calculation. Line voltage times line current times the square root of 3. 174,482, and secondary line current times line voltage times square root of 3, 172,839. But so you're within 1% of each other, and that's acceptable. Okay. Instrument transformers. The use of voltage and current transformers reduce the hazard of dealing with direct measurement of high voltages, and in addition enable voltmeters to be standardized at 125 volts and ammeters to be standardized at 5 amps. Voltage or potential transformers are simply low power versions of the normal single phase transformer. Current transformers are quite unique and special care must be taken when working on circuits using them. Current transformers convert large primary currents into small secondary currents and are voltage step-up transformers. I think that's a question on that test. The secondary is permanently short-circuited by the very low resistance of a 5 amp ammeter. The primary voltage consisting of the voltage drop across one or at least a few primary turns is very low. If the secondary is open circuited, the voltage across the primary will suddenly increase, providing a much higher voltage in the secondary, which can be dangerous to light. And we'll look at a PowerPoint that explains this a little better. For this reason, secondary windings of current transformers should never be opened in active circuits. Current transformers are used a lot. When we used a clamp-on ammeter in the lab, a couple times, and we can do it in the lab too. It's the meter that has a jaws that open. We can open it up, clamp it around one conductor, and it sees the magnetic field around that conductor, and it reads the current. And that's what these current transformers are doing. A primary difference between current transformers and voltage transformers is that the primary winding of a current transformer must be connected in series with the load. The primary winding of a current transformer has a very low impedance similar to an inline ammeter. Multi-range inline ammeters often use a current transformer with multiple secondary taps. So this ammeter here is similar to the one that you would connect in the lab workstation. We've got 0.5, 2.5, 8 amp ranges on it. The secondary taps permit the turns ratio to be changed along the ammeter to provide different full-scale values. An example shown, the meter movement requires a current of 10 milliamps to move the pointer full scale. The current transformer, however, permits the ammeter to have full-scale ranges of 0.1 amps, 0.5 amps, 1 amp, 5 amp, and 10 amps. And again, you can use the formulas to calculate the number of turns at each one of those settings on that ammeter. And we don't need to go through all the ammeter stuff. There we go. That's what an actual current transformer looks like. Current transformers are used in industrial and commercial locations for metering purposes. These transformers have a standard secondary current of 5 amps. Ratios of 100 to 5 to several thousand to 5 are common. Current transformers reduce the current to a practical value It allows common measuring instruments such as ammeters, wattmeters, bar meters, etc. to be used. When the power line is inserted through the window of the current transformer, it looks like a donut. They're called donuts. So that conductor is passing, just physically passing through the hole in that current transformer. The power line becomes a primary winding of one turn. An AC ammeter with a full-scale value of 5 amps is connected to the secondary terminals of the current transformer. Here and here, so that would be those two terminals there. The ammeter is a short circuit across the secondary of the current transformer. Assume that the current transformer has a ratio of 400 to 5. When a current of 400 amps flows through the primary conductor, so you have 400 amps flowing out here in this circuit through that conductor, the transformer secondary will produce an output current of 5 amps under short circuit. The turns ratio of the transformer can be changed by looping the primary conductor through the transformer window multiple times. If that conductor is looped through the window once, so instead of going straight through, you're looping it once and then going to get that current going through there twice for the conductor. The primary now contains 2 turns of wire instead of 1. The ratio of the transformer is now 200 to 5 instead of 400 to 5. It's not unusual to see current transformers with multiple primary turns to change the turns ratio. If a current transformer has a ratio of 1200 to 5, for example, it could be changed to a ratio of 600 to 5 by looping the primary conductor through the window once, give you 2 turns instead of 1. A ratio of 400 to 5 by looping the primary conductor through the window 3 times, and so on. In each case, the output current remains 5 amps in a short circuit condition. Although the ammeter has a full range scale of 5 amps, the scale can be marked to any value. So here you can see current transformers mounted on the incoming power commercial building. So there's 1, 2, 3 conductors where it says 400 there. That's a current transformer around this conductor. This current transformer is around that one and up there. So their current transformers are saying how much current is flowing in those conductors. Those small wires up here are then connected to the metering equipment to record the current flowing for the utility metering. The secondary winding of a current transformer must be shorted when power is applied to the circuit to prevent the transformer from becoming a step-up transformer and producing extremely high voltage. Under normal conditions, a 5 amp AC ammeter produces or provides a short circuit across the secondary winding. If that ammeter must be removed, some method must be used to ensure that the secondary remains shorted when the meter is removed. Failure to do so can cause injury or death. So we can back at the current transformer. So if you don't have an ammeter connected across those 2 terminals, and you have a conductor through there, and there is current going through it, those 2 terminals have to be shorted together, or you do have access to very high voltage across those 2.